Welcome to this video lecture. Mark Scythian, FAA licensed aerospace technician, airframe power plant avionics certified. Date today is June 21st, 2016. This video will focus on gas piston engine typical air to fuel ratios, also known as stoichiometric balance. As we went through in another video lecture, the 4 different types of gas piston engines. Regarding a 4-stroke gasoline piston engine, the leanest the air to fuel mixture ratio can exist at is 18 to 1, 18 parts air, 1 part fuel. That's the leanest. The richest is 8 to 1, optimal 12 to 1, and economy 15 to 1. With 2-stroke gasoline piston engines, they're going to run at much higher RPM, so the fuel mixture can lean out. But due to the oil content, you would think that it would be somewhat richer than it would be leaner. So the typical overall air to fuel ratio on a 2-stroke engine operating at maximum high RPM is about 15 to 1. With the diesel 4-stroke heat of air compression, the startup air to fuel mixture can stand around 18 to 1, but then as the engine increases in RPM and starts to cruise during steady speed on the road, the fuel mixture ratios can spike to as high as 50 to 1, and some applications have even gotten as high as 100 to 1 air to fuel ratio. The 2-stroke diesel piston engine exists at high RPM as well as high heat of air compression, and the peak air to fuel ratio is actually not applicable unless there is a constant RPM involved. So the typical air to fuel ratio for a 2-stroke diesel piston engine at maximum RPM could at least exist in the 50 to 1 air to fuel ratio AFR mixture. This is important to make a video about the typical air to fuel ratios for gas piston engines, because if you're too lean a fuel mixture at low RPM, thermal runaway and overheating will take place, even if you have a liquid cooled engine block. So there are cases when piston engines actually overheat even though they have a good liquid cooling system, and some people are a little bewildered why that's so. Well, if something happens with your fuel delivery system to where the mixture system is out of correct operation, usually an electronic fuel injection system has some issues with its calibration. Could happen with any type of a fuel delivery system, but if you had too low fuel mixture at low RPMs, you're going to end up with overheating. That is why when you're, let's say, in a traffic backup and you really can't get your RPMs up, you're just moving a few feet every minute or something, the fuel delivery system is going to have to richen that mixture up to slow down the combustion speed, or else the engine block will overheat due to thermal runaway. Only when the RPM goes up, then the airflow through the combustion chamber increases and aids in cooling along with the liquid cooling system, then the fuel mixture can become more lean. Also, it doesn't need that much fuel flow to give the piston a little bit of push during the power stroke. So if we focus on propane delivered into a 4-stroke gasoline piston engine, the propane will go from a liquid to a gas as low as not minus 20 degrees below zero, it'll pretty much liquefy around negative 40 degrees below 0 Fahrenheit. But when liquid propane is released out of the tank at room temperature, it instantaneously is a vapor. Now, vapors can only burn in an engine. You can't burn any liquid fuel. You have to have it atomized or vaporized first. But if you inject liquid propane in gaseous form into a 4-stroke gasoline piston engine, the RPM has to be high enough, or else hot spots will develop in the cylinder when at low RPM, and many times the spark plug will be burned out and the engine will quit. So even though the thermal efficiency is much higher with propane, it's clean burning, the carbon residue is much less than gasoline, it's actually a wonder fuel. There's only one limitation, that because it comes out as a vaporized gas at room temperature, its fuel mixture will be very lean, so you're going to have enough airflow through the engine to prevent hot spots. Now, as for automobiles that were running on LP, there would have to be a low RPM mixture solenoid that would have to incorporate a concentration of fuel for mixture enrichment, or a separate fuel like gasoline or small amounts of a applicable fuel to richen up the mixture only when at idle, or else that engine would shut down from hot spots burning out the spark plug. So it's very important to understand the fuel mixtures, especially in constant volume combustion engines such as piston engines. Thanks for watching this video, and have a good day.